Okay. Thank you everyone for joining for today's session. Good day, everyone. I would like to welcome you all to the APRU Sustainable Waste Management Global Lecture Series. I am Kumuduni Palansurya, a PhD scholar at Korea University, and I'm serving as the Secretary of APRU SWM program. Before starting today's event, I would like to invite Andrea Bibiana to provide some technical instructions for the webinar logistics for the attendees. Bibiana?
Yes, hello everyone. Thank you for being with us in the first session of Global Lecture Series. As Komunduni mentioned, I'm going to collaborate with the logistics today. Here are some recommendations to consider during the event. This is a webinar mode, so you can listen and see the panelists, and it's possible to interact with them with some tools. We have enabled 2 chats. You can ask questions to our speaker through the Q&A chat all the time, or in the general chat, you could leave comments or share important information. If you are interested to talk and ask a question, please raise your hand and I can unmute you and you can interact with the speaker directly. As this is an international event, I kindly ask you to use the English name all the time. Besides, if you have any problem, please let me know through the chat and I will try to help you. Thank you, and we hope you enjoyed the event.
Thank you, Andrea. APRU SWM Global Lecture Series is organized by the APRU SWM program, where Professor Young-Sik Ok at Korea University serves as the director of this program. This program is co-directed by Professor William Mitch at Stanford University and Professor David Wardle at Nanyang Technological University in Singapore. The first lecture of APRU SWM Global Lecture Series will be delivered by Professor Jessica Trankic from Massachusetts Institute of Technology, MIT in the USA. At the end of her presentation, there will be a Q&A session. So I encourage all the attendees to participate the event actively and come up with your questions for the discussions. So now I would like to invite Professor Young-Sik Ok to give a warm welcome to all the attendees. Professor Ok, over to you.
Okay. Thank you, Kumuduni. Hello, everyone. I'm Young-Sik Ok, who is a director of APRU Sustainable Waste Management Program and the chair of this session. So as you know, APRU has a membership of president of total 56 leading universities from all around the Pacific Rim area. This includes 2 million students, over 200,000 academic staff. So APRU Sustainable Waste Management Global Lecture Series is designed to provide a sound foundation in basic principle and unifying research across from ecology to conservation and from environmental health to waste management, while paying more attention to ESG, environmental, social and governance, and global sustainability, organized by Ojung Resilience Institute and APRU Sustainable Waste Management Program at Korea University. Particularly, some selected topics will be discussed through the APRU Sustainable Waste Management Global Lecture Series, focusing on environmental pillar at ESG. The key topic of APRU Sustainable Global Lecture Series are conservation and ecology, environmental health, environmental resource management, energy and climate change, water science, global sustainability, as well as life cycle assessment. So as you know, we, APRU Sustainable Waste Management, have consistently tried to carry out a variety of programs designed to accelerate academic activity and international cooperation. So APRU Sustainable Waste Management Global Lecture Series is a part of a regular range of events offered by the program and is designed to offer audience an inside view of cutting-edge research topic. So I believe the participant will be able to learn from and interact with world-renowned scientists around the world through this lecture series. I also hope that the event will become a valuable opportunity to extend and share friendship among those who participate in the webinar. Again, thank you very much for joining this webinar. Thank you.
Thank you, Professor Oak. Now we will move to the first lecture of our global lecture series. It's a great honor for me to introduce our speaker, who is Professor Jessica Trankic from MIT, USA. Before starting the lecture, I would like to give a brief introduction about Professor Trankic. Jessica Trankic is a professor in the Institute for Data System and Society at MIT. Her research examines the dynamic cost, performance, and environmental impacts of energy systems to inform climate policy and accelerate beneficial and equitable technology innovation. Her projects focus on all energy services, including electricity, transportation, heating, and industrial processes. This work spans solar energy, wind energy, energy storage, low carbon fuels, electric vehicles, and nuclear fission, among other technologies. Professor Trankic received her BS from Cornell University and her PhD from the University of Oxford as a Rhodes Scholar. She is currently an external professor at the Santa Fe Institute and was formerly at Columbia University's Earth Institute and at WSP International UNOPS in Geneva. So Professor Trankic, over to you.
Great, thank you so much. It's wonderful to be here, and thank you, Professor, and thank you, Kumudini, for the introduction. And I'll just jump right into the presentation, and then hopefully we'll have ample time for questions and discussion. So let me share my slides. Okay, so what I would like to speak about today is the research that we do in my lab, which is to use data-informed models to accelerate clean energy innovation. And I'm going to give you an overview of my group's research, and then I'll dive into some specific results and some recent papers that we've published to get into a bit more detail. And some of this material is going to be more technical, some of it will be less technical. I understand many of you are researchers yourself, and you have a technical background. And so, you know, there'll be something in there for everybody. And I am hearing a little bit of feedback. Is the sound okay on your side?
Yes, it works very well. Thank you.
Okay, wonderful. Good. Okay, so first, let me just give an overview of the objective of this research, which is to understand and shape technological innovation and technologies, especially in clean energy systems, in order to accelerate climate solutions and especially equitable climate solutions that are available to everybody. And that involves improving technologies to reduce costs, increase their performance. It also involves dealing with the waste that technology will inevitably create. And this is what we're trying to find solutions to. Of course, every technology has its downsides and has certain negative impacts. But the idea here is to use these models to understand how we can shape this inevitable change in technology that's always ongoing toward beneficial ends. And if we zoom into that little circle in the middle, what my research really focuses on and what's represented here is this positive feedback loop, this possibility for a virtuous cycle of emissions reductions to address climate change and technology improvement. And, you know, what we would like is also for there to be a closed cycle in terms of materials and achieving more of a circular economy. But what's really focused on here in this graphic here is this idea of, you know, at the top here, we have climate policies that create markets for cleaner technologies, capacity increases over time. And what we've seen in recent examples is that as that happens, as the installed capacity grows, there's a lot of efforts at many different levels in research labs, in companies, and a diversity of efforts that tends to lead to technology improvement. In the case of low carbon technology, we're often very interested in the costs because this is what determines competitiveness. This can then embolden leaders to adopt further policies, and this is what we did. We are beginning to see, and the Paris Agreement did mark an important milestone in that sense. But obviously, there's a lot more work to be done to reach emissions targets that have been set in order to aim to avert the worst effects of climate change, which would require drops in greenhouse gas emissions based on some targets to net zero emissions by 2015, especially in the in developed economies, as well as, and a number of growing economies have also set very ambitious targets. But we've already seen this virtuous cycle start to form. We've seen examples, I'll go over a couple of them, of where technologies have improved exponentially with time, with policy nudges. And so clean energy and these climate solutions are becoming more available. This cycle has started. And then the question is, how can we use models to keep this cycle going, potentially accelerate it, and make it more beneficial? And the methods that we've advanced in my group, since I know a number of you are researchers, you may be interested in just an overview of the methods. What we use and what we develop are bespoke, often bespoke, meaning, made for a particular question, models, quantitative models, data-informed models. They're sometimes mechanistic models in the sense that they're capturing the key mechanisms of the system, and sometimes they're data-based models, so more statistical models, to measure technology innovation, understand where that innovation comes from, and identify targets. And that is what I'll focus most of the presentation on, is this idea of targets. This is the idea of quantifying performance targets that many people can work toward achieving for given technologies that could have a large transformative impact for the system as a whole. This work is applied across scales, from materials to devices to infrastructures, and it's applied to hardware, and increasingly I'm looking at soft technology, including software and business models. Also increasingly, I'm becoming more focused on, and a number of colleagues are also becoming more focused on, the problem of the reuse and recycling of materials and dealing with waste issues. That's something that's very important. And we need to innovate toward more recyclable materials and devices. The results from this research can be grouped into two main categories. We always try to arrive at some new fundamental knowledge of the world, understanding where innovation comes from, what are some of the barriers, but then also translate that into targets for collective innovation processes, these global processes of innovation to work toward. So when I say technology innovation trends, you may wonder, what am I talking about? So let me give you a couple of examples. We now have a couple of really pretty impressive trends. And these are trends that have unfolded at the global level, because these are global markets. And Korea has been very involved with battery markets. And if we look at, let's just look at solar modules here. This is for photovoltaics. So that's the conversion of solar energy to electricity using photovoltaics. I'm showing the price trends for solar modules going back to the mid-1970s. And what we've seen is that over 4 decades, the cost of this technology has fallen by 99%. And what's underlying that are a lot of improvements to the technology, engineering improvements and process improvements in terms of manufacturing. Lithium-ion technologies have, as we just recently documented Actually, this paper just came out last week, and just today it was covered by The Economist. So if you check that out, maybe after the talk, if you're interested, they have a nice graphic detail on this paper. But we just documented the decline in lithium-ion battery costs, and they have fallen by about 97%. This is, again, based on the price series, fallen by 97% over the last 3 decades since 1991. So if you just stop to think about that for a minute, you know, basically what we're saying is that for each dollar or local currency, you're paying 1/100th of what you would have had to pay 3 or 4 decades ago for this technology. So it's a pretty dramatic decline. A lot of it was stimulated by government policy, but then that kickstarted lots of activities in companies, in research labs, and this diversity of activities. It really wasn't the story of a few people that made a few good discoveries. It was really, what we're seeing is more of a process of many activities and many people working on these technologies that led to these impressive trends. Why this is important for climate change is that now you have cheaper solar energy that's leading to major changes in markets. Solar and wind energy are the largest growing sources of electricity now. So they've basically gone from irrelevance a few decades ago to the fastest growing sources of electricity. And wind has also followed a dramatic cost decline. And these lithium-ion battery cells, these cost declines mean that they mean a couple of things. Their lithium-ion batteries are everywhere in our electronic devices, our cell phones and computers, but they're also very important for electric vehicles. These cost declines, as well as the accompanying improvements in energy density, so the the energy per and specific energy, the energy per unit volume and per unit mass, those improvements, all of those improvements together mean that electric vehicles are no longer just for the wealthy. Many more people can purchase electric vehicles with a reasonable range, meaning that they can travel quite a long distance before having to recharge. And so that's really changing the electric vehicle market. That also is important for climate change, because electric vehicles, for example, in the US, if you choose an electric vehicle today, if you switch to an electric vehicle, you can cut your emissions per mile, your emissions of greenhouse gases, by 30% or more in many places, even with today's power grid, which still relies on a substantial amount of natural gas. If we then transition the power grid to even cleaner sources, then you could cut your emissions even more. And so these are really important trends. They also show what could be possible maybe for other clean energy technologies that are needed to reduce emissions, because there's much, much further to go to flatten global emissions trends and then ultimately reduce them while improving access to high quality energy services and so forth. So there's many more challenges, but what this shows is that these processes, which were jump-started by government policy, have led to substantial improvements. There is also a real need to get better at the reuse and recycling of batteries and the recycling of materials and photovoltaic panels and systems. So that's an important area to be working on. And some of what I just said about where the cost declines came from comes from this new methodology that my group has developed to, look at a trend like this on the left-hand side. When I used to go and give talks on this and ask experts, I would sometimes do a real-time poll. And I would say, where did this cost decline come from? Do you think more of it was from government research and development funding, or more from policies to stimulate markets? And the answers would be all over the place. So we decided to take a closer look. Where did this cost decline come from? This is often held up as one of the key success stories in clean energy. So it was important to understand where that could have come from. And so what we did was develop a methodology to break down really any technology into these P variables, which are boundary prices, and phi variables, which are usage ratios. And you could see that, this kind of model can also capture substitutions of different materials, increasing utilization of materials, increasing conversion efficiency, decreases the amount of material you need. And all of that mattered. So what we did was we developed this model to understand what was actually happening at the device level that led to that 99% cost decline over the last 4 decades. And then we looked at what the drivers were for at the level of human activities. So here, this is showing research and development, something called learning by doing, economies of scale, and other. And you can see that research and development in both publicly funded, so government funded labs around the world, this is a global analysis, as well as market creation policies, research and development in private companies, as well as in government funded labs, had played a really important role. And then economies of scale was also important. It's become more important in recent decades. When we look at the policy level, we estimate that 60% of the cost decline came from market creation policies that jump-started all sorts of private sector activity, and about 30% from government funding for research and development. So that's where that's one kind of model that we developed to understand what were the drivers in the past. And then we can say, okay, going forward for individual technologies, what are the kinds of drivers at the level of engineering, at the level of company strategy, and also at the level of policy that could increase or could foster improvement going forward. And so that is something that we've looked at for many technologies, including lithium-ion battery technologies. Nuclear fission is one technology where the costs have gone in the opposite direction. Costs have been increasing in the US. I think in some other places those aren't the trends, but in the US they've been increasing. So we've looked at why that is, and that highlights some areas of improvement that are needed in order to prevent those cost overruns. Okay, and just a quick check with the organizers here. I see that there are some messages in the chat. I don't know if you would like me to answer questions as I go, or should we keep the Q&A toward the end?
Yeah, we will keep and do it at the Q&A session altogether.
Okay, great.
Okay.
Okay, yeah. Okay, so another thing that we may want to look at is a different kind of research question, which is to ask, how much better do technologies need to get? So I'm going to go over an example of that for the case of large-scale energy storage that could support the growth of renewable energy. And here, we know that costs have been falling, but how much more do they need to fall? And this picture, there's a lot going on here. I'm going to go through it step by step. This gives an overview of the method that we used in order to answer that question. How much would costs need to fall? And specifically, we want to know how much cheaper do energy storage costs have to be in order to allow for full integration, or almost 100% or up to 100% electricity coming from renewables. Now, it doesn't have to be 100%, it could be 90%, 80%, 50%. There are other carbon-free sources of electricity, but we wanted to understand what would the cost targets be for storage to support renewables at different costs themselves in order to be able to provide electricity reliably. So you might kind of think in your mind, I always like to do a little check on intuition. What do you think we need in order to be able to answer that question? You might be thinking, okay, well, I need to know, first of all, how much is the solar and wind energy resource fluctuating? And so we look at 20 years. In this case, we wanted to cover a large period of time. We've since then expanded to 40 years, and we're now looking across the entire globe. But at this point, we were, in this paper, we were looking at 4 locations in the US. We look at 20 years of data, and in each hour over those 20 years, we look at how the solar and wind resource are fluctuating. Then what we do is we set up a model of the demand for electricity based on these traditional roles that power plants play today, which can be combined to meet the overall demand. We then model how storage would perform in order to support renewable energy and help meet those grid roles. Then we say, well, what about if we want to combine solar and wind to minimize the cost? And we see that usually a combination of the two is preferred in all locations that we looked at in the US. So we looked at high wind locations and low wind locations, high solar, high and low solar resource locations. But in all cases, there is a preference for combining the solar and wind in order to minimize the cost. And then we look at, and this will be important, we'll get to this in a minute, but then we look at, well, what if we reduce the amount of renewables or grow the amount of renewables that we're relying on? We might want to rely on something else for part of the time. What does that do to the costs? And then finally, what can we say about how inexpensive storage costs need to be? And how does that compare to where they are today? So I'm not going to spend a ton of time on going through all the details of this because I want to leave still a bit of time for the next part of the presentation, the next example, but let me just quickly go through the results. So what we found was that what really defined the cost targets for storage were these large but rare events where there was very little sun and very little wind for some extended period of time. So imagine 10 days where the wind is below average, or in some places it's above, it's very high wind so that it's above the cutout speed for the wind turbines. And these are these events here where the state of charge of the battery drops below 50%. But you can see there's only a few of these events over 20 years when we're using solar. And similarly, when we're using wind, there's just a handful of these large events. And when we combine them, again, there's just a small number of these events. And so if you really want to meet the demand for electricity all of the time, all of the demand using renewables, then you're going to be needing to install a lot of storage that would be where its capacity wouldn't be fully used all of the time. Now, that's not necessarily a deal breaker. That's something that is done with peaker plants today, but it can add to the cost of the system. So what does this mean for the cost targets? Well, when we look at, and let me just walk through this plot. When we look at this, and here on the right-hand side, what we're seeing is the levelized cost of shaped energy. And we want to get down to this blue region. That's where the cost, and the dark blue region is where we would reach cost competitiveness with today's sources of electricity. We looked at these 4 locations: Texas, Massachusetts, Iowa, and Arizona. So Arizona, for example, if you have been there, it's known for its sunshine. Iowa is known for its wind. In all of these cases, we're using the optimal mix of solar and wind based on cost minimization. And the bottom line is that what we see is that the storage energy capacity cost is what's really important. You need to be able to store a lot of energy capacity. You need very long duration storage that can last for many, many hours. And because of that, the storage energy capacity cost target is around $20 per kilowatt hour. So to give you some context, that would represent about a 80 to 90% decline in costs of batteries relative to where we are today. So it's a pretty substantial cost decline. On the other hand, if we say that we'll meet the demand for electricity just 10% of that demand for 10% of the time with some other source, then those cost targets come down dramatically. They rise dramatically, they become less stringent. So then we estimate there are cost targets that are closer to $150 per kilowatt hour, which is relatively close to where we are today. with batteries. But then it begs the question, where are you going to get the additional 10% from? Is this going to come from demand management? Another option is to expand transmission infrastructure, or it could be from a low carbon fuel source like hydrogen that's maybe being made from carbon-free electricity sources. So there's still some research to be done on that. But basically you can see, if we just focus on this top row and we focus on the baseload solar, let's say, any of them is fine. But if we look at this, you can see that if you reduce the amount of renewables you're using from 100% to 95% or 90%, you have these pretty significant cost declines. And that's really what is changing that cost target that I mentioned. And that's basically because you might have guessed, but where that's coming from is that you're using something else other than relying on the energy storage during these extreme events. So that's something that was an interesting and somewhat surprising result. And it's also informing a lot of work that's going on right now in developing new storage technologies, as well as informing other research on, other alternatives like demand management and transmission infrastructure expansion. Okay, so now let me move on to another kind of target, which would be for electric vehicle batteries. So what about for electric vehicle batteries? How close are we to where we need to be in order to satisfy the demand and the energy needs of vehicles that are driving around? And here we wanted to look at how can we meet the energy demand in vehicles such that we're not causing any inconvenience, so that people would be able to, stop where they're naturally stopping. Today, we wouldn't delay them and so forth. And we wanted to know, just for a daily snapshot view, how many of these vehicles could be replaced with a low-cost electric car and still meet their daily requirements. And so what we do there is we set up a model to look at the demand for energy in vehicles. So there we need to look at different households, and we're looking across the US in this case. We want to know how far they're driving, and then we're going to look at the vehicle model and see, how far can the vehicle get them? How far can they go before they have to recharge? And from there, we're going to estimate how far batteries would need to improve further. So we'll skip over that. And to do this, we need a very detailed model, because the range of a car is not a single number. It depends on what kind of road you're driving on. It depends on what sort of vehicle. Is it an electric vehicle? Is it a hybrid vehicle, a plug-in hybrid, or an internal combustion engine vehicle? So we have to take all of that into account. And in order to do that, we needed very detailed data on how people are driving. But what we had was some detailed data, and this is pretty common across the world. There's often smaller data sets that are very detailed temporally. So we might have second-by-second data for how cars are moving around in space. That's important because we need that to accurately estimate the amount of energy they need for their trip. And then we have more coarse-grained data that is in travel surveys, but that covers the entire population. What we did was to develop a probabilistic matching model so that we could expand the set of GPS surveys to match the travel survey so that we could cover the entire population, and then estimate the energy distribution of these vehicle days across the entire population of vehicles on all roads in the US. And this is something that required a lot of validation and testing to make sure that the model did well, and it turns out that it does. And I'm just going to show you this picture. So basically what we want to know is how cars are moving around on a second-by-second basis across all of these roads. And so this was what we wanted the model to do. We needed a vehicle model. We needed to, and this has been tested. And then we needed to do this kind of matching so that we could arrive at these, what are called drive cycles for all of these trips across all of these roads. And what we found was that we were able to develop a model that had a very high accuracy. So if we were just to use the published data from the US, the Environmental Protection Agency rating of fuel economy, then the error per trip is about 20%. But if we apply our what's called the trip energy model with that probabilistic matching procedure that I mentioned, we can get the error down to 7%. And that's only a little bit higher than the error we get with only our vehicle model if we assume we know the GPS drive cycle. So basically, we can get a very accurate estimate. And then now I'm going to show you the answer, which, and you can think about what you think the answer is. I'm not going to ask you just in the interest of time because we have one more example to get through. But you can think about, okay, if we look, I don't know how many people are very familiar with the US, but if we look at, let's say, the entire country, and we look at the picture of cars driving around on a daily basis, we say, how many cars on a given day could be replaced with a low-cost electric vehicle and meet the driving needs of that vehicle without having to recharge during the day? And the number was a little bit surprising. It's about 90%. So it's a very high number. That represents about 60% of gasoline. But there's another interesting aspect of the results, which is that we discovered there's this heavy tail of high energy days. So the remaining 10% of vehicle days that can't be replaced by the electric vehicle consume a disproportionate amount of energy and gasoline. And they're also much harder to replace with an electric vehicle without some creative solutions. We also know that, you know, most people have these high energy days. So if we take a longitudinal picture instead of this cross-sectional one that I presented, most people experience these high energy days. So if you want to give people confidence that they could purchase an electric vehicle, they'll need to know what they can do on those high energy days. Another interesting finding was that the number was remarkably similar across very different kinds of cities from Houston to New York. So Houston in Texas is a very sprawling city, and New York is a much denser urban area. And people tend to own less cars in New York, but when they do drive, there's a certain similarity in how they drive to how people drive in Houston, such that the distribution across those two cities was quite similar. And this number of vehicles, the daily adoption potential was quite similar. Another conclusion from that analysis and that heavy tail distribution is that as you improve batteries, and here we're improving the battery energy density and the specific energy, so you're packing more charge into a given mass and also volume, you start to get diminishing returns. So you have to improve the battery so much more in order to cover the needs on those high energy days. And we know that batteries are improving, but this led us to ask, well, what about other solutions like charging infrastructure? So this is the final example I'm going to give, and then we'll open up for questions, which is to look at charging infrastructure. So in this final example, what we did was to look at how cars are moving around in space. Again, we looked across the entire country, and then we did a detailed analysis for Seattle. And we're also working on collaborations of this kind to look at this sort of thing in other places as well. We have a collaboration in Indonesia, for example. And so what we wanted to do was to understand how people move around, where they stop throughout the day, for how long they stop, and how this changes for them throughout the year, because we wanted to capture those high energy days. And we want to see, well, where would you have to install charging infrastructure in order to meet people's needs on high energy days? And just to confirm again that we have these high energy days, if we look at the right-hand plot, And the reason I'm showing, by the way, the Nissan Leaf is meant to represent a lower cost electric vehicle, and the Tesla Model S is a more expensive electric vehicle with a higher battery capacity. But you can see that there's this heavy tail of high energy days, because you'll notice that this is a log axis. And so the question is where to put charging infrastructure to deal with that. On the left-hand side, I'm just again confirming that in this case study of Seattle, you have a very different energy intensity per mile for this battery electric vehicle, depending on how someone's driving. So again, that very detailed model, that second by second data on movement in vehicles is important. And so to look at this, what we did was we gathered this data. I mean, someone else actually gathered it, but it was a public data set that looked at, it followed people, a large number of people for a year, and looked at where they're, when they're driving, where they're stopping, for how long, and so forth. So they may be parked at home, they may be driving, they might be parked at public locations for shopping or dining, or at a bar, and then they're driving again, they may go to work, that sort of thing. So it followed all different people in the Seattle area, and we then confirmed also these results to the extent that was possible with data for the US as a whole. And so what we learn, just quickly, I want to go over the main results here, is a couple of things. So now I'm going to introduce a new metric, which is this metric VEP. That's the vehicle electrification potential. That's the number of cars that could be replaced, the portion of cars that could be replaced with an electric vehicle and still meet their needs over an entire year. So no longer just one day, but the entire year, under different charging scenarios without causing them any delays. So they're charging only when they're stopped naturally, as they would drive today. And we assume chargers are located in different locations in order to understand where they could be most impactful. So one thing that you'll notice is that, for example, if we only have chargers at work, then the vehicle electrification potential is quite low, because people, this doesn't cover all days. Most people don't work every day of the week, or they don't at least go to the office every day of the week. And I mean, certainly not right now, but even pre-pandemic and post-pandemic times, there's often weekends and so forth. Or if they're not working in offices, wherever people are working, in manufacturing plants, et cetera, there's usually some downtime. And if we put chargers at home, then you can raise that number. So that number gets above 10%. And then if you put chargers everywhere, you get to above 20%. But even if you put chargers everywhere, which isn't a very realistic solution, you still can't get up to like 100% for the low cost vehicle, nor can you do that for the higher cost vehicle. So then what about if, this is just for level 2 chargers, but what about if we put fast chargers, 150 kilowatt fast chargers? Well, then you can see that you can get up to a higher adoption potential or a vehicle electrification potential of above 40%. So that's pretty impressive. What could we do to increase this number further? Well, you can see that if we add the capability of just a couple of days where you would rent or borrow or somehow gain access to a long-range vehicle, then you can increase VEP quite substantially. This is for 10 days, and we also look at 4 days. And then if we combine home, work, and fast charging, as well as a couple of days a year access to long-range vehicle, then you can get up to 60%, 80% of vehicles being electrified. And so that's interesting. And this led us to this final chart here, which is about this idea of how would we then combine infrastructure for charging in order to enable the electrification of vehicles. And if we focus in on the lower cost electric vehicle with the 40 kilowatt hour battery, you can see that one of the most promising charging strategic packages is to combine home charging, work charging, highway fast charging, and then overnight public charging at places like hotels. And by the way, the home charging here doesn't only mean home charging in private parking spots. It should also apply to residential areas and public parking in residential areas. And then you can get up to about 50% vehicle electrification potential. You can get these numbers up to above 90% of vehicles that could be electrified if you supply access to additional supplementary long-range vehicles on at most 10 days a year. So basically, this is an example of how we used, and we can just show this little video again of these cars moving around, but this is an example of how we use these data-informed models, considering behaviors, considering technology limitations, considering kind of the places where people stop as part of the behavior, and also considering how technologies may change in time in order to arrive at some priority locations for installing charging infrastructure, which would be close to residences, at work. The reason for that is because of the electric power grid impacts, fast chargers along highways, and some overnight locations like hotels. And then also what's critical is access to supplementary vehicles on a small number of days. So that's the end of my examples there. I'll just quickly go through some examples of how this research informs decision-making by engineers, private investors, policymakers, and the public. And one way is to inform engineering design of low-cost energy storage. There are a lot of startups and more mature companies that are competing in the grid scale energy storage space. And so having these cost targets out there has informed some of their work. This work is also informs private investment. So private investment firms have referenced this work. We also wrote a report on this, this work and the findings on that virtuous cycle, that reinforcing cycle of emissions reduction technology improvement, and presented it to the Obama White House before the Paris negotiations. And this concept and this report of covering a mutually reinforcing cycle in which enhanced mitigation increases investment and enhanced investment allows additional mitigation by driving down costs. This was cited in the official press release of by the White House on the Paris Agreement after it was signed. And then finally, we try to put tools out there that can inform the public. So this is an example of one. It's called carboncounter.com. We released a new version in January. You can check it out, carboncounter.com. The name is here. And it was covered by the New York Times in this nice graphic. It's something that allows people to check the cost and the emissions of their of vehicles they may be considering buying. And this is where we can see the much lower emissions of electric vehicles. There's a lot of work to do in being able to recycle batteries and, generally recycle materials. There's a lot of material being used and waste being used up here as well. And this is for the US market. I should mention that in some Asian markets, there are electric vehicles that are much, much cheaper that are available. They have lower range, but it's interesting because there are some big differences emerging across the different markets around the world for what kinds of cars are available. So anyway, that was my research at a glance. And I think I will now be happy to take your questions.
Okay,
Thank you.
Yeah, thank you very much for your presentation. It was really impressive. So we have 10 minutes for Q&A, and I see there are actually a lot of questions. So let me ask at first, Dr. Yuan gave some detailed question through the chat menu. So could you please ask your question to Professor Jessica?
Yeah.
First, thanks for your great talk, Professor Chancy. I'm Xiangzhou Yuan from Ojedi Korean University. So for the data-driven models, the data collection and the pre-processing are pretty critical process. So my first question is how to efficiently distinguish the useful data out of all collected data? And the second one is there a limitation on those data-driven models for solving the existing problems? Thank you.
Yeah, no, I think you're touching on a really important issue, which is that we don't always have the data we need to solve these most important questions. We sometimes have data on tons of data. We tend to have more data on the energy consuming behaviors, for example, of consumers in more expensive cars, but that's just covering one segment of the market. And it doesn't help when we're thinking about climate change mitigation, where it's a society-wide shift. And there are all sorts of issues, as you mentioned, with data quality. So with all of the work that we do, we're very careful about getting a handle on and estimating quantitatively the data uncertainty, and also making sure to validate wherever possible the results with multiple different data sets. So that's really key, is to understand the data uncertainty and the data limitations as much as possible, and try to keep validating as new data become available as well. So that's one thing. So model validation is, against the data is really important, but also data validation is also important in estimating the data uncertainty. And then, I do think there are limitations in data-based models, what you're calling data-driven models, which is also why I mentioned that we focus on data-informed models, and some are mechanistic. Those are different from the database models. Those we test the results against data. So, but they're not statistical models, or they're not based on machine learning. Now, there's really interesting research in machine learning that's getting at causality and so forth. So I think that these two areas may begin to merge, but certainly for what we do and with the data that we have available, we try to do both database models and also mechanistic models and theory development.
Thank you.
Thank you, Dr. Yuan. And we have actually 3 questions from Hwang Gonuk and Tabani from currently in Germany, and from Kumuduni. So Kumuduni, the 3 questions look like quite similar. So can you combine and ask the question from your side?
Yes, Professor. Thank you very much, Professor Trankik, for your interesting presentation. Actually, this question is based on your paper published in Nature Energy. In that paper, you assessed the potential solutions to meet personal vehicle energy requirements with battery electric vehicles. So, and also you found that home charging can support energy requirements approximately 10%, and highway charging can raise it up to 40% and so on. So our question is that these regular travel activities may change over the time, and especially during COVID-19 period, these regular travel activities can change. So we would like to know your viewpoint on these changes, and do you have any data on the changes of these potential solutions? Thank you.
Yes, so yes, thank you so much. It's a great question. What I can say is that for the US, for example, where we have data across subsequent years, this phenomenon of high energy days is present in across all of these different years. In fact, the distribution of vehicle day energy requirements is quite similar as we go from one year to the next. I think this has to do with certain kind of natural habits that humans have. It also has to do with the diurnal cycle and other constraints on the system, where most people have certain days where they want to travel far distances, but in most cases, for most days, they don't want to drive X number 7-8 hours, right? Now, it's still, though, during COVID, what we see is that transportation is down across the board. And then, I mean, it was down and then it rose, recovered in a number of places, and at different countries around the world, this kind of these dips and these, the rises, the recoveries and so forth have been timed a little bit differently. But there have been some changes during COVID. On the other hand, this probability, I expect that we still have some high energy days, because, you know, there are certain circumstances, especially now as people are becoming vaccinated in some locations more than in others. I mean, I have not been vaccinated yet. I'm looking forward to it. But people are still wanting to travel far distances. So I expect these high energy days, to the extent that they've fallen, they will recover to some extent, you know, and probably back to their pre-pandemic levels is my guess. Now, I see some of the other questions are about the, and did I answer your question, Kumadini?
Yes, Professor.
Okay.
Thank you very much.
I did want to,
Thank
thanks. And I did want to kind of look beyond the US, because of course, the question is, are these high energy days present in other countries as well? So far, we're seeing that they are. In some places, like small island states, of course, there's a physical limit on how far you can go. Like, you're not going to be like driving around the island several times. You would just go you know, I mean, you might, but that would be rare. But in, you know, even so in Indonesia, some of our initial results based on surveys we've done are that there are also high energy days there. So it does seem to be a more general phenomenon, but it's something that we'd like to look at. And then looking at some of the other questions, there were some questions about, is it okay if I just go through the answers, the questions in the chat? Does that?
Yes, please. Thank
Okay,
you.
yeah, I'm sorry, I left only a little bit of time, because you know what, I was monitoring the number of questions in the Q&A and there was only one. So I thought, oh, there's not too many questions, I'll keep talking. But I see now there's some questions in the chat. So yes. Yes, so here we can see, are these models accessible and implementable for different countries? Yes, I mean, to the extent possible, whenever we develop these models, one of the reasons why we focus on mechanistic models and on theory and fundamental understanding is to be able to understand answer the question why, where are the results coming from? And then we can more easily say, okay, what part of that answer why would be different in different locations. So you can imagine if I just did the simulation on what charging infrastructure would work, and I never tried to study the energy distribution, I wouldn't know why we were getting the results. And then I wouldn't know what to look for in different countries in terms of the differences in the energy distribution. So what we see is that the models, yes, they can be applied anywhere. Some of the solutions will be different depending on where you are in the world, what country, and so forth. Long-range vehicles, we looked only at light-duty vehicles in the study that I presented, but we are looking at long-haul heavy-duty vehicles. And for some portion of these vehicles, I believe electrification with battery electric vehicles is a good option. For heavier trucks, the jury is still out whether batteries will work, or clean fuels like hydrogen could be better. That's something that we're looking at. And then the last question, I guess, just in less than 1 minute, is about the impact of COVID on renewable energy markets. I think, you know, I expect renewable energy markets, I mean, I think they're growing in, you know, that you're still seeing strong growth based on the data that I've seen. I mean, we can see some fluctuations. I expect that, you know, to the extent that climate policies stay in place, we'll continue to see growth in renewable energy markets. And the main challenges in achieving carbon neutrality by 2050, I would say the most difficult challenges still remaining. There's improvement needed across the board in all technologies, but long-haul heavy-duty transportation, including air transport, shipping, is one challenge. We need to be working on fuels for that. Heavy industry, steel and cement manufacturing, we need solutions for that. It could be carbon capture and storage and other approaches, but there are certain industrial processes that are difficult to electrify. So those are some of the main challenges. And then, you know, a third one could be that very long duration storage that I presented. We need some more innovation there, combining that with transmission infrastructure expansion and demand management. So those are some of the main remaining challenges. So the list is getting shorter, and that's good news.
Okay, so thank you very much for your kind answer for all the questions. And it's exactly for the 9 a.m. in Seoul, so it's the end of the webinar. So Kumu, can you kindly conclude the session?
Yes, Professor. Thank you very much, Professor, and thank you very much, Professor Tranky. And this is the end of the first session of Global Lecture Series. So I would like to extend my sincere gratitude and appreciation to Professor Tranky for your valuable contribution and for sharing your knowledge with us during your busy schedule. So I also extend my special thanks to Professor Young-Sik Ok for organizing this wonderful event. Thank you all the panelists and the program leaders and all the participants for attending this event and bringing your expertise to this gathering. So thank you again. I wish you a great day to all of you. Thank you very much.
Thank you. Have a great day. Thank you, Jessica. Bye-bye.
Thank you so much. Thanks for having me. Thanks.